I pass it over to Bruno for his talk.
Thank you very much for the introduction, Vlad, and the kind words. Gonna share my screen and get started. So, hi everyone. As Vlad mentioned, I am Bruno. I am a second year PhD student here at UBC under the supervision of Scott McDougall. And in the next minutes, I'd like to describe some of the key research avenues that we're exploring in advancing tailings and breach analysis. And I'll start with a brief introduction of tailings, rheology, and the mining industry. Then I'll mention some of the insights that we discovered from the rheology compilation, and then draw some remarks for what is expected from us in the next years. And I guess continuing the conversation that we had about tailings and breach analysis this morning, it is important for us to make a distinction right away to look at these materials not only within geotechnical structures such as tailings dams or tailings stacks, but with the broader perspective of an integrated system that goes from the mineral extraction all the way through tailings deposition. And within each of these phases, a bunch of operational and environmental factors come into play to distinguish the characteristics and impacts of tailings. And one huge impact of tailings in the environment is when a tailings storage facility fails. And because of that variability that I mentioned from both environmental factors but also anthropogenic factors, the behavior of the tailings runout can be vastly different from case to case. And that's certainly the case here when we compare the fluid-like behavior of this mixture of tailings and water that resulted from an overtopping failure in Zambia earlier this year with the clearly non-Newtonian behavior that we see here from the Feijão failure. And we see the lateral levee formation and an intense soil erosion from this high-energy debris flow phenomenon. And given this diversity, there's one fundamental common framework that helps us understand scientifically what's going on, and that's rheology. Now, the study of rheology can be quite complicated when we open textbooks and we see lots of differential equations and fancy words like these ones that I'm showing. But it's interesting to note the evolution of these subjects that now constitute the backbone of rheology, from Archimedes in the antiquity and Newton in the 17th century, talking about idealized, perfect rigid bodies to descriptions of material properties by Einstein in the early 1900s to the formal definition of rheology. And then in the mining industry, this evolution is related to different testing methods, which then suit different applications. What works for pipeline design may not capture the behavior we need for tailings runout modeling. But then rheology studies the behavior of matter undergoing deformation, and it is used by a lot of different fields outside engineering. And I really love this image. These authors, they compared one fundamental concept of rheology, which is yield stress, to the shear strength of soft foods. And then we can appreciate the wide variety of behavior under deformation that tailings that are represented here by these gray bars can have, from deforming like condensed milk to behaving like a peanut butter. And then, of course, this difference of behavior makes it challenging for us to simulate and predict tailings dam breach events. Now, rheology comes into play not only when we analyze the runout behavior of tailings in motion, but also from different requirements within the mining industry. The watering requirements from processing plants to pipeline energy calculations to the optimal depositional angle that forms in the tailings storage facilities. And all of these different mechanisms are analyzed in rheological testing. And then we, as practitioners, interpret the results that come out of these tests. And rheology research specifically for tailings dates back to the 70s. But even though there are many publications out there, there still seems to be a gap when it comes to bringing together all of these different perspectives in an integrated approach, as well as the key characteristics that govern the rheological behavior of tailings, especially for tailings and breach analysis. So with this in mind, the need for a central database of rheological properties of tailings derived from experimental tests, my research team at UBC has been compiling rheological properties of tailings from many, many publications dating back to the 70s all the way through today. And what we're doing is analyzing different variables and asking many questions. For example, can geological and geotechnical characteristics such as mineralogy, ore type, grain size, tailings classification be good predictors of rheological characteristics? Can we see any patterns in yield stress and viscosity, which are two really common input parameters for tailings enrich analysis, when we analyze the factors that govern the rheological test, such as the test method or the shear stresses and strains applied. And this is just one example of a trend that we're seeing. And these are preliminary results of a viscosity values of dozens of publications categorized by the geotechnical classification of these tailings. And then you can see here that within the same volumetric concentration range, coarser tailings have orders of magnitude lower viscosity than fine and ultrafine tailings. And then when we further incorporate more parameters and analyze through the lenses of other elements, other cool patterns emerge. But then for dam owners, even without rheological testing, knowing your tailings classification can help bracket expected flow behavior within these orders of magnitude. But then that begs the question, how does this data and these patterns converge to better practices in tailings enrich analysis? There are many insights that we discovered, much more than the time allows us to share today. But the first that I'd like to point out is the difference between static and dynamic yield stresses. And then in a simplistic definition, you can think of yield stress at the yield stress of a solid being essentially the point at which, when increasing the applied stress, the solid first shows a liquid-like behavior or a continual deformation. And then some publications that analyze the temporal evolution of stresses in tailings rheology advise us to differentiate between the peak static value where a fully viscous behavior emerges, and then the residual dynamic yield stress, which represents kind of a static flow condition. And this is backed up by decades old publications that exemplify this reduction in yield stress as from 10,000 pascals to less than 200 pascals following mechanical agitation. And this mechanical agitation can be thought of analogous to liquefaction, and thus this differentiation is important for tailings enrichment events where susceptibility to liquefaction is expected. And curiously, mechanical agitation is one of the steps that pretty much all published experiments report doing before conducting the actual rheological test. On tailings, this is necessary due to the complex, non-ideal, time-dependent nature of these materials, and especially due to tailings and mineral suspension being heterogeneous and containing solid particles that tend to settle over time, especially at low concentrations or during transportation and storage delays. And then mixing becomes essential to prepare a homogeneous sample and ensure that solid particles are suspended uniformly within the liquid phase prior to the rheological measurement. And then mixing and conditioning is just one of a series of steps necessary for rheological testing in tailings. Sample handling is very important, and the representativeness of sampling for a tailings enrich analysis is key. Unfortunately, key steps such as mixing and conditioning and the isolation of fluid phase, which is necessary for eliminating measurement errors and also ensuring homogeneity, can move away from all of these steps can move away from the high complexity of many tailings enrich events that we see that are often multi-phase chaotic events. And as with any other engineering test, traditional rheological tests have these shortcomings, and we need to be aware of that when conducting tailings enrich analysis and mindfully adopting correct test procedures and choosing the correct parameters. And then when transporting this consciousness to tailings enrich runout modeling, we need to make sure that currently used numerical models are associated with the correct input parameters to then generate reliable output results. And there are many other variables that influence these events, especially when more detailed studies are expected. And then our simulations must account as accurately as possible the initial hydrological conditions of the watershed, the flow behavior under the chosen rheological constitutive equation, and then possible complexities with runout, such as the dilution in water bodies or interaction with infrastructure. And then here at UBC, along with lab experimental results, we're also collecting reported best fit results from tailings dam breach back analysis, and also found interesting results that build on previous work from our group. But then what are the next steps that our work and our field demand? Well, this rheological work is on its final stages, and we're planning to publish the database of all of the rheological values that we are collecting in the form of a dashboard in the upcoming months. And we then want to take these insights to more advanced computer modeling and investigate the relationship of these rheological values with some more physically based input parameters and modeling strategies. This video is an example of a finite volume method model of a landslide entering a lake. And then you can see the overtopping of the mass flow entering the lake and the erosion of this drain downstream, which in this simulation was completely governed by physical constraints and involving pore pressure. This main investigation has the goal of approximating measured material properties, whether them being rheological, geotechnical, hydrotechnical, with reliable input parameters for more accurate runout predictions. And then last but not least, BGC and many other actors are fundamental in making these future steps possible. So a huge thanks to BGC and each of our partners for making this research possible. And thanks very much for your attention.
Hi, Bruno. Thanks so much for that presentation. I see we've got at least one question in the Q&A here. So it says, Buen dia, Bruno. It's quite interesting from the literature review the variety of yield stresses of various tailings, from as low as 0.007 pascals to what looks like 10 to 100 times higher for something like FFT. What tailings are these, from heavy oil extraction or from heavy metals?
It's lovely to see some Portuguese here. Thanks. These are the results that I've shown are from tailings from all over the world, from all over, so related to all sorts of mineral extraction. So, mainly iron tailings, copper and gold, but also fluid fine tailings, such as the ones that you mentioned, Chi. And then we're also collecting other mine waste materials. So not only traditional tailings, but also red mud, for example, or backfill for slurry transport and deposition. And so a bunch of materials, but then in the dashboard that is soon to be published, you'll be able to filter out the materials that you're interested in. And then if you're interested in oil sands, you can just see the yield stress variations or viscosity variations of oil sands.